Hello. Now we could come to the second lecture on the photoelectric transducers, which till now we have seen the photocells and the photomultipliers. Now we come to the third class of photoelectric transducers, that are photoconductive cells. As we know that in the semiconductor material, the free charge which are in the conduction band are, if they are available, they can be used for conduction by applying simply the electric field. Okay, now there are certain semiconductor material where the electron can be jumped from valence band to the conduction band by simply applying light of correct wavelength. So, and by applying that voltage, we can find we can take a current from them. This shows that the resistance of semiconductor decreases with the increase of light intensity. Okay. Therefore, these semiconductors are known as photoconductive cells or photoresistor or sometimes light detecting resistor. There are certain material also which if by the increase of electricity or by increase of intensity of the light, we can change their resistivity or change their conductivity. They are known as light detecting resistors. Now, the two most commonly used photoconductive materials are cadmium sulfide, that is CDS, having a band gap of 2.42 electron volt, and second is cadmium selenite, that is CDSE, band gap of 1.74 electron volt. The photoconductive cell use a special type of construction which minimize the resistance and which provide in the maximum surface. Photoconductor cells are made by chemically sintering the required powder of CDSE into a tablet of the required shape and enclosing them in a protective envelope of glass or plastic. We simply do a sintering of these two materials on a conductive plate, and this in the form of tablet, and these are encapsulated in a glass or a plastic, so that we use glass or plastic so that the light energy can enter to the photoconductive cell. Let us see the figure of this. First of all, let us see the construction. Okay, electrodes are deposited on the tablet surface and are made of material which gives an ohmic contact, but the low resistance compared with that of photoconductor. Gold is a typically used. So electrodes के लिए normally we use gold so that the have a material which is having a low resistance, and the gold is one of the best example to make the electrode. The electrode are usually interdigital, that is in the form of interlocked fingers or comb as shown in figure. Something like this. They are simply interlocking construction. You can see the figure. I'm enlarging this. It is something like that. Two combs are interlocked in between. And they are having leads coming out of that, and this is encapsulated in a plastic or a glass material. Okay, and this comb shape is nothing but it is made up of photoconductive material. Okay, the side view is something like this. That was a top view. This is a side view. There is a glass window from where the light is being entered, so to encounter with the photoconductive material. The characteristics of photoconductive cell are vary considerably depending upon the type of material used. Their characteristics are given below. These are some of the materials. You can see that cadmium sulfide, cadmium selenide, lead sulfide, lead selenide, and they are having a time constant of 100 millisecond, 10 millisecond, 400 microsecond, 10 microsecond. Spectral band that can be used for these materials are given in the table. So these are the characteristics of some of the photoconductive cell. Now, when the cells are kept in the darkness, when they are kept in dark, its resistance is called dark resistance. It should be as high as 10 into 10 to the power 12. When they are kept in dark, their resistance should be having these values. The resistance depends on the physical characteristics of the photoconductive layer as well as on the dimension of the cell and its geometric configuration. The resistance totally depends upon these three parameters. Okay, the dimension of the cell, the geometric configuration, and the characteristic of the photoconductive layer which we are using for the COM structure. Okay, the current depends on the DC voltage applied, and the current flowing through this photoconductive layer, that totally depends upon the applied voltage. The current is in order of milliampere, that normally is in the 10 to the power minus 3 range. Now, photoconductive cell. The spectral response characteristics of two commercial cells are shown in the figure below. These are some of spectral characteristics, which is simply the relative response with respect to the wavelength. For different wavelength, how the response is being seen for two different, that is cadmium sulfide cell and cadmium sulfoselenide cell is shown over here. Curve 1 is for cadmium sulfide cell and curve 2 is for cadmium sulfoselenide cell. Okay, now there is almost no response to the radiation of wavelength shorter than 300 nanometer. From this curve, you can say that below 3 nanometer there is no response. And cadmium sulfide cell have a peak response in the green part of the spectrum at 510 nanometer and can be used in the near IR region up to 750 nanometer. This is the property, or this is the parameters of cadmium sulfide cell, and the maximum response of cadmium sulfoselenide is in the yellow-orange region at 615 nanometer. This can be used in the IR region up to 1000 nanometer. These are the two most commonly used photoconductive cells. Now, the sensitivity of the photoresistive transducer is given by S is equal to delta R by delta H. Delta R is nothing but the change in resistance, and delta H is nothing but change in irradiance. Okay, the ratio of this gives you the sensitivity of the photoresistive transducer, or you can say the photoconductive transducer. The spectral response of the sensor must match that of the light source. Whatever the spectral response you want to measure, that should be totally responsive with the light source. And it is common for a photoconductive element to exhibit a resistance change of 1000:1 for a dark to light irradiance change of 5 into 10 to power, sorry, it's 50 watt per meter to, I think it's, sorry, it's 5 into 10 to the power minus 3. Okay, irradiance change of 5 into 10 to the power minus 3 watt meter to 50 watt meter. Okay, this point is saying that there should be a resistance change for light to dark, of that should, its ratio should be 1000:1. Okay, and with the change of irradiance, that means 5 into 10 to the minus 3 watt per meter, that is the dark region, to the 50 watt meter, that is the light region. If there is a change of such much irradiance, then the resistance change should be in the ratio of 1000:1. Okay, now the relationship between the irradiance and the resistance is however non-linear, and normally given by this relation over here, which says that RT is equal to nothing but Ri plus Rf minus Ri in the bracket and multiplied by 1 minus e to the power minus t by tau, where the RT is the resistance at a particular time and Ri is the final resistance after application of beam, and Rf is the dark resistance. Okay, and tau is your time constant of the material which has been used in that forming the photoconductive cell. So this is how the relationship of resistance with the irradiance. Okay, and it is totally, as there is an exponential component over there, we can say that it is a totally non-linear relationship. The disadvantage of the photoconductive cell: the temperature change causes substantial resistance change for a particular light intensity. If there is a temperature change, there will be a lot of change you will be seeing in the parameters. Therefore, this type of photoconductor is unsuitable for analog application. Therefore, analog application in the analog application there is a lot of variation of temperature. Therefore, it is not used over there. Most of the time it is applied for pyrometry for quantitative spectroscopic measurement. Now let us see an example. A cadmium sulfide cell has a dark resistance of 100 kilo ohm and a resistance in a daylight beam of 30 kilo ohm. The cell time constant is 72 millisecond. Find the resistance of cell after 10 millisecond of application of beam. Okay, there is a cadmium cell whose dark resistance is given to you and time constant has been given to you. Okay, find the resistance. We have to find the resistance after 10 millisecond of application of beam. When the daylight beam is producing a resistance of 30 kilo ohm, we simply use a standard formula which we have studied above and substitute the value of R, I, R, F and all the time constant. You will be getting 39 kilo ohm. Photodiode basically it is simply a PN junction diode, and its electrical characteristics are almost as a rectifier. As we know that PN junction diode, when we apply P with a positive voltage and N with a negative voltage, it is in the forward bias, and when it is opposite polarity is being applied, then it is a reverse bias. Here at the radiation at the PN junction cause of flow of current shows a current shows in the circuit of the photodiode, which we will be seeing in the next slide. So in this case, in the PN junction diode, this special type of PN junction diode, we see that the reverse saturation current varies with the intensity of the incident light. The reverse saturation current photodiode is worked in a reverse bias condition. So the reverse saturation current varies with the intensity of the incident light. Let us see this in the circuit. You see that this particular diode is applied with in the reverse bias, and there is a load resistance. So as the radiation is increasing, the diode current, the saturation current is increasing. Okay, there is a figure which shows a typical characteristic of photodiode, which we'll be seeing in the next slide. Photodiode is applied where we have a area restriction. If we want to deploy a phototransducer in a small area, the best option is photodiode, because the effective area of photodiode is about 0.2 millimeters square. It's quite small, and it is a pinhead. It is almost a pinhead, so as an electrode of diameter of 0.5 millimeter. So it is very helpful in the case when you have to implement it for a short area. Now, the photocurrent versus light relationship is almost linear over a wide range. To maintain the linearity, the voltage should be kept constant. The bias voltage, the reverse bias voltage should be remain constant. As soon as it remains constant, the linearity is maintained. Let us see the characteristic curve. The characteristic curve for different irradiance, that is for 25 watt per meter square and 50 watt per meter square and 750 watt per meter square, there are different irradiance. For that, the photocurrent versus reverse bias voltage is shown. We can see that for a wide variety of range, it is linear, and after some time it becomes saturated at certain value. Okay, the frequency response of photodiode is largely dependent upon the intrinsic capacity. Now, as we know that a diode can be worked as a capacitor too, because one is positive plate and one is negative plate. It can be worked as like that also. So the frequency response of a photodiode largely depends upon that capacitor due to a semiconductor or intrinsic capacitance. The capacity is typically of 2 picofarad for a reverse bias of -10 volt. A typical value of 2 is given there, that when you apply a reverse bias at time -10 volt, 2 picofarad, there is a value. The cutoff frequency can be calculated from that. It will be 1 by 2 pi RC, and where R is the load resistance and C is the photodiode capacitance. The cutoff frequency is of megahertz range. So from the load resistance and photodiode capacitance, we can find out the cutoff frequency of a photodiode. Let us see a numerical on this base on the above relationship. The question is saying that the effective area of a photodiode is 0.2 into 10 to the power minus 6 meters square and irradiance is of 250 watt per meter square. Calculate the incident power. If the load resistance is 10 kilo ohm and the capacitance of the diode is 2 picofarad, find out the cutoff frequency. Okay, let us see further. If the incident power is given as 250 watt per meter square and the incident power into the 0.2 into 10 to the power minus 6 is multiplied, you will be getting 50 microwatt, so, which is multiplied by the photodiode effective area. So the effective power can be calculated for the photodiode area, which is 50 microwatt. The cutoff frequency F0 is equal to 1 by 2 pi RC. So we simply calculate that simply by putting the value of R and C. The value of R is given as 10 into 10 to the power 3 as 10 kilo ohm, and C is 2 picofarad, that therefore it is 2 into 10 to the minus 12. After calculating, you are getting 8 megahertz. So this is how the incident power and the cutoff frequency is calculated for a photodiode. Let us see next transducer, that is photovoltaic transducer. Photovoltaic cell or a barrier layer cell consists of a 3-layer as shown in figure. A base plate B, a semiconductor plate S, and a thin transparent metal layer T. Proper processing produces a thin insulating barrier layer between the semiconductor and the metal layer T. If the light is incident on the barrier layer, an EMF is developed across the base plate and the top metal layer, with the base plate being the positive terminal. This is how the construction of a photovoltaic transducer is done, and working of the photovoltaic transducer has been explained. Now, a thin film of normally gold or platinum is deposited as a crystalline selenium with a base plate of iron. This is a normal configuration, and presently the cells with silicon and germanium for semiconductor layer are available. They are also known as photojunction diode. Now, let us see the detail, the working principle of this photovoltaic cell. When the incident quantum of light is absorbed by the barrier layer, formation of electron and hole pair take place. The electric field in the barrier layer causes the separation of the carrier, and hence a change in generated between carrier, and hence a charge is generated between the semiconductor and the metal layer. Now, a charge can either flow back through the barrier layer, setting an internal current, or can cause flow of current in the external circuit connected to the terminal. This is how the working of the photovoltaic cell will be done. Since all the energy of the current is derived from the light source and the cell acts as an energy converter, the current through the of measurable magnitude represent very small power. Okay, the short circuit current is proportional to the area of the cell, the effective area of the cell, it depends upon that, and increases linearly with the luminance. As soon as you are increasing the luminance, the current value also increases. The graph is shown below, and which is for short circuit value, it's a straight line, and as you are giving a load to that 50 ohm, 100 ohm, 150, and it is getting little bit non-linear. This is the current value with respect to light flux. Now let us see the characteristic become non-linear. The above characteristic which we have seen, that it become non-linear when illuminance is very high. Only a part of the surface is exposed to the light, and lastly the load resistance. As we have seen in the graph, as you are increasing the load resistance, the curve is getting more non-linear. Now the sensitivity of this photovoltaic transducer is on order of 1 milliampere per lumen. The open circuit voltage increases in the logarithmic fashion as shown in figure, and is independent of the cell area. As you are increasing the light flux, the voltage, open circuit voltage, is increasing logarithmically. It is found that when the incident light flux is increased by 1000 times, the resistance of the cell falls by 100 times. You are increasing the light 1000 times, and the resistance is decreasing 100 times. This is a spectral response of a selenium cell, which is almost similar to that of your eye. It is between 250 to 750 nanometer, which is the visible range, and maximum response is seen at 570 nanometer. Okay, which is almost similar to that of our eye. Now, response of some other cells, germanium is primarily in the IR region responsible wavelength to the 200 nanometer near UV2, with the maximum sensitivity around 1500 nanometer. The silicon cell has its threshold wavelength of 1200 nanometer. All the above cells area are also sensitive to alpha rays, beta rays, and X-rays. The generation of EMF within the cell takes place with a microsecond after exposure to the light, but the build up of the output voltage is delayed by the large internal capacitance of the barrier layer system. Okay, current generation takes instantly, but the voltage generation takes some delay due to the capacitance of the barrier layer. The germanium cells are the fastest, and the selenium cells are the faster than the selenium cell in their response. The fastest is Ge cell. All the above cells are affected by the temperature. How the temperature is affected? The voltage and current decrease rapidly with increase in temperature. If you are increasing the temperature, the voltage and current value get decreased. With this, we have completed the photovoltaic cell and all the photoelectric transducer. In the next lecture, we will be seeing the piezoelectric transducers.